Otherwise, our first session is on language ideas and language-driven insights from Ego4D. You all hopefully have the program, and today is Ego4D, tomorrow is Ego4D, and session 1 is a combined set of 4 talks that have built on Ego4D and language. And we're starting by Kevin from NUS. Feel free to start when convenient.
Okay, thanks, Dima. Okay, can you see my screen?
We can,
okay.
And we can hear you clearly.
Okay,
I'll
nice.
stop you if you go beyond 10 minutes, otherwise have fun.
Hi everyone, my name is Kevin from NUS and I'm supervised by Mike Show. And today I'm very honored in here to present my recent work, VLOG. Video language models by generative retrieval of narration vocabulary. First, I will start by how existing video language models work. Those models usually import video and make a conditional query and produce a textual response. And those models usually connected to a LN's vocabulary. Those vocabularies are mainly from the language corpus. And those vocabulary size usually being large, such as 38K in Llama 3, and it is based on the subword levels. However, in the video scenarios, we found that those subwords usually be incomplete, such as HAPP and length of visual meanings. And also the token-wise generation, such as cut a potato, being slow in the inference time. So we are very clear about what kind of the video assistant we are produce. Instead to have a perfect model can capture anything, we may prefer to have a custom video model then customized on our daily life. So it means it can produce the concise contextual response in a real time. So we imagine how humans organize their experience, such as when you record your whole day, it can be briefly divided into a serious behavior. And we think that those behavior can be treated as event levels vocabularies. So we are curious about, can we borrow this idea to power the video language models? So the key idea of our work, VLOG, is that we assume that the daily videos can be logged by the event vocabularies. If we assume we have such a vocabularies from the video dataset, such as Ego4D, so then if we want to produce a response, such as cut potato, we may need a less token numbers, such as only 1 token. And instead of the generative token sequence, we can translate this problem as a retrieval problems. So then it can be more very efficient. So this introduced 2 research problems to achieve this goal. The first is the model, and the second is the how to define such a vocabulary. And I will introduce each kind of mainstream models respectively. The first one is the generative models. Those models usually start by the language models, and they will project the visual tokens into textual space, and based on some query. And such fashions is good at model the complex reasonings. However, it being slow for token by token generations. Well, the second kind of method is that assume if we have such a narration vocabularies, we can reuse the clip style model, such as a video clip or EgoVLP, and then we just need to simply perform the alignments. So then, such as the cut a potato is the vocabulary for this video. This is fast, but it will be few to model the reasoning relationships. So our idea is want to include both the advantage by either the generative model as well as the retrieval model. So based on the generative model, we introduce a new memory tokens. It followed by the previous inputs. And then after the language model projection, it will attend the previous observation. And later, this memory token will be used for the alignment. It will be used to align the one of the target vocabulary in the vocabulary set, such as based on this video and what's the next action condition. The oracle's vocabulary is watching the potato. And this model is trained by the contrasting object. So it can maintain both the advantage from the generative model as well as the retrieval models. And the next question is, how should we devise such narration vocabulary? Well, the Ego4D's narration being the ideal choice as it has the word diversity, and its narration is a well-modeled event levels activity. However, there's still some problem, such as narration is usually being subjective, such as they may start by different ending, but had the same meanings. Well, in NLP, the people will use the byte pair encoding to define a new vocabulary, but it cannot directly apply in our scenario since we want the narration level vocabulary. So we propose new solutions, namely narration pair encoding. Its key idea is that we will treat each narration as a potential prefix, and then we will search for the longer narration, then start with it. Those longer string will be treated as the postfix. So based on this transformation, we'll have the prefix set and the postfix set. And we based on the Ego4D, we create a 0.6 million prefix and 5K postfix. And the next issue is that as a narration being large scale, such as medium level, it will slow down the retrieval speed. So how to speed out the retrieval times? And our idea is that we found a video action usually recorded in a particular scenario, such as cut potato is usually in the kitchen. So based on this relationship and the annotation on the Ego4D, we can use the scenario tag to narrow down the search space. So then we can speed out the retrieval time. And once we have the model and the vocabularies, the next is how should we prepare data to train the model? As the previous video text pairs is usually for symbol alignment, and there will be few to model the reasoning relationship, such as what's the next action or previous actions. However, we found that the untrained video string being the ideal choice as it naturally models the temporal relationships. So we can model such retrieval data, such as even for the same oracle text vocabularies, but we require model condition on different visual input and different credit and to retrieve the same one. And based on this strategy, we construct a video vocabularies development set with two settings. The one is the navy retrieval, the previous ones, and the second is the causal retrieval. It requires to have the temporal reasonings. This is the retrieval data set, not the generative one. And now let me highlight the key advantage of by our vlogs. In this development set, it required the model to produce the accurate narration and as well as being fast. Our vlogs is able to produce the accurate narration in both settings, in navy retrieval as well as a causal retrieval. This result is comparable with the retrieval methods as well as the generative models. And more importantly, it can maintain the fast inference time compared with the retrieval-only methods. And it can achieve 20 times speed out compared with the generative method, which perform the token-by-token generations. And this is more significant when we apply to the longer videos. And here we show some example how our vlog works.
I have 1 minute.
Okay. Given such a video content where carries, vlog will first navigate the target scenario, such as doing the yard work. And then it will enter the preview subset belong to these things. And it will retrieve the top one prefix, and that later retrieve the top one postfix. And then you will connect the prefix and postfix to being the complete narration, and this being the response. And this is another example with the same video content, but under the different narration, different query as condition, our vlog can retrieve the different response and satisfy our goal. And there's still one issue in our framework as we need to construct a cross-set vocabulary. So we also develop a generative workflow. It will recall the generative model, such as the Lava 1 Vision and LM, to help us expand the vocabulary side. So then we can adapt to the novel event that not appear in our original vocabulary. And that's all my today presentation, and thanks for your listening.
Thanks for sharing. Just to say, this work is yet to come on ArXiv. Any questions? We have time for a couple of questions. Antonina.
Thank you for the presentation. My question is, how does this scale to the case in which, let's say, you train on a data set and then you test on another data set in which you don't just have a few out of vocabulary actions, but everything is out of vocabulary. So like there is a very small overlap in vocabulary. So let's say you train on people cooking and you want to test on people, I don't know, like doing some other activity, like fixing a bike or something like that.
Yeah, in our evaluation, I not display here. We have experience about the out of vocabularies, and in these settings, we will select some videos, such as coin or the high rest. It's not it have some novels novel actions such as the barbecue. That do not appear in the Ego4D. So we use it to test the out of vocabulary, and it also is not egocentric.
So do you get a drop in performance? I guess you do, but how much?
Yeah, I think our goal is not to reach very good performance in those settings. We want to propose a strategy to, such as we can use our vocabulary, use this framework to improve performance, to improve the vlog's generability to the novel events.
Great. Can I ask, Kevin, if you can stop sharing? Mohammed can share his screen for the second talk, and in the meanwhile, if there is another question, we can take it.
Okay.
Any question from panelists or attendees? You need to raise your hand. Otherwise, great. We remain on time. Thanks a lot, Kevin. And again, much appreciated. I know it is past midnight, so I'm glad you're contributing. Next talk is again yet to come on ArXiv, and that is presented by Mohaiminul Islam from UNC Chapel Hill. You are muted.
Can you hear me now?
Now we can. Go ahead.
Yeah, thanks, Dima. So hello, everyone. I am Mohaiminul. I will present our work, BIMBA, Selective-Scan compression for long-range video question answering. So recently we have witnessed a lot of interest in multimodal large language models, and we have also shown impressive results from image MLLMs. However, existing video MLLMs have not progressed that far, and it can only process short video of few frames, like 8 frames. So in this project, we want to develop an efficient video multimodal language model that can process long-range videos and more frames. So for that, we want to utilize the Selective-Scan state space models. So first, let me give you a overview of the state space model. So state space model is a sequence-to-sequence model, which can be described by this simple equation. Here, X is the input sequence, H is the hidden state, and Y is the output sequence. So this is a very efficient alternative for self-attention, which has linear memory and computation cost, as opposed to quadratic computation cost of self-attention. However, one of the drawback of the standard state space model is that here the parameters A, B, C are constant and time invariant. Therefore, they don't have any way to explicit selection from the input sequence. So recently, a improved version of state space model has been proposed called Selective-Scan state space model, which has been used in Mamba LLM. So here the difference is that now parameters B and C are input dependent. So now the model has a way to selectively propagate or forget information, and they have been also shown successful in various tasks. For example, in their paper, they have shown the advantage of this Selective-Scan mechanism in this artificial task. So here, you are given a sequence of tokens, and only some of the tokens are marked, and you need to output only the marked tokens. So basically you need to select these important tokens from your input sequence. So here you can see that S6, which contains the Selective-Scan mechanism, achieves much better performance than standard S4 or state space models. So in our project, we ask ourselves a question like, can we utilize these properties in video domains? Because long video especially is also very redundant, and it has many redundant frames or tokens. So can we use this mechanism to select important frames or tokens from the videos for question answering? So utilizing this Selective-Scan model, we propose BIMBA, an efficient model for long-range video question answering. So given a long video input, first we encode each video frames using a image encoder and extract patch level tokens. Then we employ a spatiotemporal token selector, which reduces the sequence of spatiotemporal input tokens by more than an order of magnitude, for example 16 times. Then we pass these compressed tokens along with our language question to the LLM to generate the answer. So here we present more details on the spatiotemporal token selector. So first, from the long sequence of spatiotemporal tokens extracted from each frames individually, we initialize some visual queries using a 3D adaptive pooling layer. So this pooling layer, after the pooling layer, the number of tokens reduces by orders of magnitude by, for example, 16 times. However, this pooling provides a good initialization for our queries, but it cannot capture like fine-grained details within the video. So therefore, afterward, we employ the Selective-Scan selector, token selector, which has a layer normalization, a linear projection layer, and the Selective-Scan layer. So it also has this residual connection. Through this Selective-Scan layer, now it can combine fine-grained details from all the spatiotemporal tokens and add those details into our visual queries. Finally, only these visual queries are passed through the LLM along with our question to generate the answer. So that's the model design, and we also explored some other design to improve the model architecture. So first of all, so this is the standard way of adding queries. So we can just add all the queries at the end of the sequence. However, this approach can introduce bias because it positions queries to the later portion of the video, and it limits the interaction within the earlier frames, thus missing details from the beginning of the video. To address this, we propose a interleaf query positioning where we position the queries equidistant inside the spatiotemporal tokens. This design enables interaction within the tokens from all parts of the video, supporting a more balanced and comprehensive representation. Moreover, the original Selective-Scan developed for 1D sequence is suboptimal for vision task since it lacks spatial awareness. To address this, we apply a bidirectional scan which performs a forward and backward scan through the visual tokens. This enhances model's ability to capture spatiotemporal structure present in the video. Thus, it is more effective for video tasks. So we train our model on 378K instruction tuning data aggregated from a collection of dataset. We did not use any data generated by GPT-4, and consequently our instruction tuning data is substantially smaller than prior works. We evaluate on 7 diverse benchmark from MVBench, which contains only a videos of 30 seconds to like video MME or MLView, which contains video of up to 2 hours. So we also compare with 4 baselines. So vanilla, this baseline removes the spatiotemporal token compressor, so it does not perform any compression. And for pooling, self-attention, and perceiver, we implement these baselines by replacing the Selective-Scan layer from our model with this corresponding sequence modeling layers. So here, first, we show the performance on Ego4D and next QA as a function of number of tokens or frames, where we experiment with from 1 frames to 64 frames, resulting in this many tokens. So we can see that the vanilla and the self-attention model quickly goes out of memory, and we can only experiment with a smaller number of frames. And efficient sequence model like perceiver or pooling is suboptimal, especially for pooling. The performance even drops for a very long sequence. But our model BIMBA can maintain high accuracy, and its performance improves monotonically as we increase the number of tokens. So we also compared the memory and efficiency. Here we can see that vanilla and self-attention goes out of memory, also showing the quadratic cost of self-attention. Pooling and our model maintains lower memory cost and also lower runtime. Here we compare our model with the state-of-the-art models in all these benchmarks. We can see while using the same backbone and same number of instruction tuning data, our model achieves better performance than other strong baselines like PLAVA or Lava Next Video. Moreover, it also achieves state-of-the-art performance in several datasets, even with a lower number of data, such as like for Ego schema. So here, we also show some qualitative result. We can see that our model can answer questions of different types, such as fine-grained details in the videos or like high-level overviews of the video. Here is another examples. It can also show you like the steps from cookings. Yeah,
Thank you.
that's
Very
all, everyone. Thank
These
you.
might be difficult to read on the screen, but hopefully when this comes to archive, people can see the examples. There was a
Okay.
first question from Ria on the length of the videos. I guess you mentioned that depends on the data set, right? So this is trained per data set?
So, sorry,
Is it a different model for each of these data sets, or is it one model?
it's one model. Yeah, we have a collection of 378K instruction tuning data. Yeah.
So maybe what's the length of these models, or Leah, if you have further, so what's the length of models in training, the length of videos in training?
Oh, so for the length of videos of training are at most like 3 to 5 minutes. So they are a few seconds to at most 5 minutes.
Okay, any other questions? Right. So let me ask one. So this Mamba, thing, and we keep seeing these visualizations that show scalability.
Yeah.
So compared to things like Perceiver, where indeed you're still learning something, representing the sequence, what is the advantage here? What's the core of the additional difference to something like Perceiver that cross-attends to all the data and learns a small level? Is it the temporal causality?
Yeah, I think it's the temporal causality. So since the Mamba has this it's a sequence model to all the sequence. It has this advantage in like capturing this temporal relation from this longer sequence compared to something like Perceiver.
Okay, cannot see any further questions. Thank you very much. Nice presentation. We move to Toby, who is presenting work that will be presented at ACCV next week.
Hi, can you hear me?
Yes.
Can you see my PowerPoint?
Yes.
Great. Okay. Okay, I'll make a start. Yeah. So thanks everyone for coming. This is our work. It's just another day, unique video captioning by discriminative prompting. And this is by me and Dima at Bristol and Tender and Andrew at Oxford. So I'm going to start off by saying life is repetitive. We encounter lots of similar places and events, such as traveling to work, doing the dishes, and so on. And currently, video captioning approaches, they tend to generate the same caption for similar clips because they tend to treat these clips independently. So here's some egocentric footage. We've also got some footage here from a time loop movie. And this one's called Edge of Tomorrow. Don't know whether people have seen it, but Tom Cruise fights some aliens, dies, wakes up again and relives the same day over and over again. And again, you get this problem with the similar captions. This can be a problem either if you're trying to do a text-based search with these captions, or whether you're just trying to make them interesting, for example, for audio descriptive captions for the visually impaired. So our goal is, given a set of clips, can we generate a unique caption for each of them? And this set might be a long video, it might be the result of a retrieval against a database or something like that. So what do we mean by unique captions? Well, we can visualize captioning as a mapping between visual space and text space. And here we don't have a one-to-one mapping. We can go from videos to text, but we can't go back one-to-one from text to video. In this paper, what we do is we look for a kind of property for a video clip that allows it to be defined uniquely. For example, what the person is holding in the pink clip allows it to be uniquely identified. But this might not be possible for all clips. So if we can't find a unique property, we're going to advance in time until we can find something that is unique about them. Okay, so before I describe the method, I'll give a quick recap of how video captioning works, though you probably all know this anyway. I'm going to take our video clip, feed it through a captioner, and we'll usually just get a response, one token at a time. And as a reminder, prior captioning methods, they tend to perform this operation separately for each clip. So this is why you end up with non-unique captions, because there's no communication really between them. So in this work, we're going to use fixed prompts to direct the captioner to focus on certain aspects of the clips. And we're going to call these discriminative prompts, as we'll use them to help distinguish between clips. In this case, by prompting the captioner to look at where the person is walking around, we're directing it to look at the environment. So, say we want to do these two clips. Rather than just use one discriminative prompt, we're going to use a bank of them, which allow us to get a diverse range of captions for each clip. For example, for egocentric footage, we're going to have 10 fixed prompts. This one will, for instance, pick up what's in the environment. This one might pick up what the object the person is holding and using is, and so on like that. Now, to generate unique captions, our goal is to select the best discriminative prompt for each clip. So the way we're going to do this is first we're going to run them through a captioner to get responses. And now we want to see whether these discriminative prompts are any good. So if we have a look at this one, we can check out its caption. So the caption is the person walks around a building site. But then we can check against this video and see, oh, there's also a building site here. So this one isn't very good. Let's look at the next one. We can see what the person's holding. It's a screwdriver. But it doesn't appear in this clip. So we know that this is a good discriminative prompt. And we can do the similar process for the yellow clip. Importantly, notice how when we're choosing them, these discriminative prompts, we're actually looking at both clips. First, we generate from the pink clip and then check against the yellow clip. And this idea of discriminative prompts is what allows us to condition on all clips instead of just captioning them independently. So we've solved it. We just have to consider clips jointly and use a bank of discriminative prompts. But this is a very expensive process because you have to auto-regressively caption every clip with every prompt, and nobody wants to do that. And another question is, what if there isn't a suitable prompt? Say the clips are nearly identical, the method won't work. So instead of this expensive auto-regressive captioning with every clip, with every prompt, we're going to train a network which we're calling CDPNet, for captioning by discriminative prompting net. And we're going to directly predict prompts. And it's trained on hundreds of thousands of similar clips and captions from Ego4D. And importantly, instead of auto-regressive captioning, this is just one single pass through a lightweight network. So scale's much better. And then say you get a clip where you can't tell a discriminative prompt from. This is where we're going to do our temporal advancement. So we'll advance a few seconds. And because this is lightweight, we can run it again very easily. And that's how it works. So benchmarks, we're going to introduce two benchmarks. For Egocentric, we're going to take clips from Ego4D with the same narration in sets of 10. I'm just showing 3 here, so they're big enough. So this clip 1 and clip 2 might come from the same video. This clip 3 might come from a different video. And these two are actually very difficult, so you might need some temporal advancement. So that's our data. The task that we're going to do is, for every clip, we're going to caption it. And then we're going to evaluate, firstly, how well the videos retrieve the text, and then how well the text retrieves the video. And this is a good way of checking for a nice one-to-one mapping. So let's have a look at the first clip. Ideally, it would retrieve its own caption. And ideally, this would happen for every clip. And in this case, the video text call at 1 would be 100%. But in practice, you might, for instance, have multiple clips not retrieve, or this clip might not retrieve its own caption. It might retrieve this caption instead, in which case you've got 2 successes and 1 failure. So your recall here is 66%. We can look at it the other way as well. So look at text to video retrieval. In an ideal world, everything would retrieve its own video. But in practice, you might end up with only 1 working correctly, and this would be 33%. Then all we do is we just take the mean of the video text and text to video, which in this case would be 50% as an overall score.
2 minutes.
So time-loop movies, we're going to do the same evaluation process, but we'll have a quick look at the data first. Time-loop movies, as I said, is a movie where the same event happens over and over again, but with slight differences. So they're a really good test of being able to distinguish between clips, mainly because they're designed to be similar. And this is a movie called Run Lola Run, and the person runs around a street corner lots of times. So in this case as well, you'd need some form of temporal advancement probably to answer the question properly. So quick results. We're going to use our average recall at 1 metric, where higher is better. We're going to take the visually conditioned language model from La Villa. And we're going to take it on its own, then we're going to add our approach to it. And this plus 0 seconds means we're not doing any temporal advancement. We're limiting it to just the original clip, and you get an improvement there. And then as you do more temporal advancement, the results improve. And we run it with a video capture or movies as well, and you get similar kind of behavior. So let's look at some examples. So I'm going to show a set of repeating clips from the movie Groundhog Day. And this is, so you've searched for the clip where the man lies in bed. We're going to see how our method augments these captions. And in these, I'm pausing the video when it said it's found a unique element. And we can see you get a nice one-to-one mapping between what's there, between the text and the video. Here's another one. This is from the movie A Map of Tiny Pretty Things.
Might want to skip this and just present the ego because we run out of time.
Yep, and then some egocentric examples as well. This one's easy to answer because it's just what the person is holding. This one's more difficult as these two clips are very similar. This one manages to pick up that it looks at the list, but with this one you have to wait before they pick up the packet of cough rubs before it finds something unique. And then finally, this selection of prompts allows you to select combinations of prompts. So with this last clip here, if you just look at picking up a plank of wood, the model might confuse it with this clip here. And if you just pick up hold a nail, it might get confused with this clip here, but the combination of the two is unique. So in conclusion, visually similar clips are common, they happen everywhere. The key point is that to generate unique captions, you want to condition on multiple clips, and CDP, our method, provides a method to do that with these discriminative prompts. And we've also done 2 benchmarks, one based on Ego4D and one on time loop movies. And if anyone is interested, there's website and code and paper and everything. Thanks for listening.
Thanks, Toby. Questions?
I feel like I'm in a time loop movie of AZ writing papers on Run Lola Run.
We're introducing him to Ego4D alongside, so we're doing it. Now he's into both of
I
them.
think I've had these for about 20 years now. So, but nice work, nice work. Okay.
Thanks. Yeah, it's interesting because there aren't actually that many time loop movies. There's only, well, we chose 10 because they were with enough repeating clips, but he's used them before loads for diagnostic stuff.
As soon as you said this, I said, okay, Run Lola Run is going to come next, and after that, we have Groundhog Day, and you performed completely to expectations.
Thanks.
We can ask, I'm trying to figure Zheng from UNC to share, and if there's any final questions to Toby. Yeah, Toby, you might want to stop sharing, so yeah.
Cool. Hi, everyone. Can you hear me?
We can indeed, and we can see
Yeah.
your.
Oh, cool, cool. So let me share. Let me present it. So yeah, my name is Zheng. I'm a PhD student at the UNC Chapel Hill, and I'm working with Professor Getas Bertasius, and I'm going to introduce our work, a simple large language model framework for long-range video question answering. So this is already accepted to EMNLP 2024. Yeah. So here are the motivations for our work. So firstly, most existing video models only focus on short videos, for example, less than 1 minute. And if the video is more than, for example, 3 minutes, such model will probably fail, probably produce wrong predictions. The second one is that the current long video understanding models often use complex designs, such as memory queue or state space models. Such complex designs are hard to implement and also hard to build up on, I think. And the last one, so large language models have shown very impressive capabilities for long-range reasoning. For example, long document understanding, long horizon planning. And in our work, we are interested in exploring this one. So how to leverage large language models to design a simple, training-free, yet effective model for long video understanding. So that is our motivation. So this is the overall framework of LoV. So basically, LoV consists of 2 stages. The first stage, we sample short clip from a long video. So as shown on this figure. So this video is a 3-minute long video. We first divide the long video into multiple short clips. Then we use a visual captioners to take the caption from each short clip, and that is the stage 1. And in stage 2, we simply input all the captions and also the question we want to answer to the large language model and ask the large language model to answer this question based on the captions. So yeah, this is our overall framework. So we also propose this multi-round summarization prompt. So this prompt also consists of 2 rounds. So the first round is to prompt the large language model to summarize the raw captions. So our intuition, yeah, as shown on the bottom left figure, so you can see the captions. So each one corresponding to 1 second clip. And if the video is 3 minutes long, there will be many such captions. And our intuition is that such captions are very repetitive. For example, if the person is cutting a potato, this actually cannot be finished within 1 second. Maybe the person will spend, for example, 30 seconds to do this thing. So, and probably the caption will be 30, the person is cutting the potatoes, such captions repetitive for 30 times. And so large language model can be easily affected by this repetitive information. So basically, in the first round, we just summarize, we input all the repetitive captions to the large language model and ask it to give us a summary of this video. So that is the first round. And in the second round, we basically input the summary to the large language model for question answering instead of the raw captions. And we believe this summary can help the large language model for reasoning. Yeah, so our model is mainly evaluated on this Ego schema dataset, which is a very long form video question answering dataset. So this Ego schema dataset contains 5,000 multiple choice question answering pairs, and the average duration of each video is 3 minutes. So unlike many previous long range video question answering based benchmarks, this Ego schema dataset requires analyzing visual cues from the full video to answer the given question. So the authors has carefully designed the questions to enable this. So for example, shown in this figure, so on the right, this is a 3-minute video, and on the left, the question is, what is the overarching behavior of C and the man in the video? So you can imagine to answer this question, the model really needs to analyze almost every frame. So as a comparison, many prior long video question answering benchmarks, so their question designs are not enabling this property. So for example, the prior benchmark, the question might be, so is the person indoor or outdoor? So to answer that question, maybe only a few frames is already enough. The model do not need to analyze all the frames. So this is a very nice property of this Ego schema dataset. Yeah, and here are the main results of our model on the Ego schema format. And firstly, we can see that compared with the previous state-of-the-art method, our LoV method actually has a large improvement. So you can see compared with Vamos, there's a 3.9% improvement in terms of the QE accuracy. And also LoV is 2.2 times faster than other large model-based methods, such as Vlog. But this is a very early version of Vlog. I assume Kevin improved it a lot, and they have a new version of it. So yeah, and lastly, we can see that our proposed multi-round summarization prompt also outperforms the standard prompt by a very large margin. So on the format, we can observe a very significant improvement, like a 9.4%, which shows that our summarization prompt is very effective. So yeah, we also perform some empirical analysis on this Ego schema subset. So this table shows the influence of different visual captioners. So actually, the visual captioners has a very strong, very significant impact on our model's performance. As shown in the figure, you can see that the best one is this La Vela captioner, which is trained on egocentric videos, and the accuracy is 55.2. And we also tried a few other frame level captioners, such as Lava and Blip2, but their performance is much lower than this Lavela captioner. And we also tried this Oracle captioner, which means, because this Ego schema dataset is from the Ego4D dataset, and it actually has the narrations. And we take out those narrations of the captions, and we input those narrations to the larger model. And that is our Oracle experiment. So we can see that this Oracle experiment performance is much higher than other captioners. Yeah, this means our model can always benefit from the future development of the visual captioners. So basically, the stronger the captioner is, the stronger our model is. Yeah, and this table shows the influence of the large language model in our framework. The choice of large model also has a significant impact. So yeah, shown in this figure, we can see that GPT-4 as the large language model gives us the best performance. Oh yeah, I'm sorry. Yeah, GPT-4 gives us the best performance and outperforming GPT 3.5 and the Llama 3 17 billion. So this also shows that the stronger the LLM is, the stronger our model is. That's a very nice property of our framework. So in this table, we explore the video processing configurations because we need to sample short clips from the long video. So in this table, we divide the long video into multiple short clips with different lengths. We explore the influence of the clip length. And so in this table, we can see that when the clip length equal 1, our performance is the best. When the clip length equal 8, the performance drops a little bit, but not much. We can see the performance is 53.4, only like 2% drop. And in this table, we explore the clip sampling rate. So we divide the long video into multiple short 1 second clip, and we sample a clip. We do not sample every clip. So for example, if the clip sampling rate equals 1 divided by 8, we sample 1 second clip every 8 clips. So that will be much more efficient than sampling every clip. But in this table, we can see that if the clip sampling rate equals 1 divided by 8, the performance will drop. I'm so sorry about this. I'm so sorry.
Okay.
Yeah, the performance will drop, but also not very much. And in this table, we explore the different variants of our multi-round summarization prompt. So the first variant is called C2S. Basically, when we summarize the raw captions, so we only use the caption as the input. And the second variant is called CQ2S. So basically, when we summarize the raw captions, we also give the LLM the target question. And we believe maybe this question can guide the direction of the summary. It can give us better summary. Maybe in the later stage, it can give us better answers. That's our intuition. And the third variant is called CQ8S. So basically, we also give the answer candidate to the larger model to do the summarization. So yes, in this figure, we can see that the variant of CQ2S actually gives us the best performance, and the CQ8S, the performance drops a lot. So we assume this is probably because answer candidates are very noisy, and this can maybe distract the summarization process. And the CQ2S also outperforms the C2S and the standard prompt by like 3%. Here we compare the multi-round summarization prompt with other prompting techniques, such as chain of thought on the Ego schema subset, and we can see that it outperforms the chain of thought prompting, and also the plan and solve prompting. So those experiments are done on Ego schema dataset, and we also evaluate our model on NextQA and the intent QA dataset. So on the intent QA, on the NextQA dataset, you can see that Lovi outperforms the prior SOTA method by a significant 10.2%. And on this intern QE dataset, we can see that LOVI outperforms the prior SOTA method by 6.2%, which is also very significant. We also extend our framework to next GQE dataset. So basically, the next GQE dataset asks the model not only to answer the question, but also gives the frames which are relevant to answering that question. So on this dataset, we can see that LOVI also outperforms the prior SOTA method by a large margin, like 9.3%. And this shows that LOVI framework can be used to temporarily ground the predictions to the visual content for more explainable long-range video understanding. Yeah. So here are the conclusions. So we present the LOVI framework, which is a very simple, training-free, yet effective large model-based framework for long-range question answering. And LOVI achieves SOTA results on multiple long-range video question answering benchmarks, such as Eagle schema, NextQE, and intern QE. And LOVI also achieves state-of-the-art results on grounded video question answering benchmark, the next GQE dataset. And finally, we thoroughly evaluate various design choices of our approach and analyze the key factors behind the success of our method. So yeah, that's my presentation. Thank you.
Thank you very much. This work was presented at, or will be presented, I don't know when this conference is, at EMNLP.
Yeah. It's already presented at the EMNLP 2024. Yeah.
Excellent. Any questions? Can you go to the bit where you're presenting the different language models, the strength of the language models? Because I was trying to understand how the language models, maybe I missed that, how do the language models outperform your Oracle? Or have I missed, or is it like this is the language model put into vision? Or maybe I missed that bit.
Sorry about it. For this experiment, I'm actually not using the Oracle, the Oracle captions. So I'm using the Lavela captions. So yeah.
So do you think, what do you think? Because I think like the performance is still like, is that we're not getting there. Imagine you get the Oracle captions. Do we have any idea of how far we are with these stronger models?
I see what you mean. So basically, this Oracle experiment used GPT 3.5. So Oracle captions plus GPT 3.5. The performance is 66. And so yeah.
Expecting a 11% increase, you think? Maybe, at least, or if it's, so it's 11% between 55 and 66 on GPT 3.5.
Yeah, that's a 11% improvement for GPT 3.5. And for GPT-4, I'm actually not sure about the exact numbers, but I assume it will be pretty big. So
how expensive was this?
So depends on your clip sampling strategy, actually, because we sample clips every 1 second, and we use all the clips. That will be many captions. If you reduce the sampling rate, maybe you use less captions. That will be less expensive, and I think But if you use all the captions, I assume it will be a little bit expensive. Yeah.
Anyone with final questions to Zheng or any speakers in the first session? Yeah, I'm probably biased. I did like our narrations in particular too much. So my bias has resulted in the first session being language driven. It's amazing to see what these narrations have done to the improvement of ego and language models and the type of benchmarks we've produced as a result. If there are no questions, it's time for a deserved break. We are back in 20 minutes. So whatever your time is, 20 past rather than 5 past. It's 5:05 here. I guess everybody else is different timing. So we're back at 25 past for the second session. We don't have the first speaker. I'm afraid they have an emergency, but we will have talks on task graphs, and then we will have the open mic discussion. So thank you very much. Thanks especially to the speakers of the first session, and see you shortly. Okay, we are ready to restart if people are around. Let's give them a minute. And I think Ivan is going first, right? If you want to test your screen.
Okay. Okay, do you see the screen? Do you hear me? Should I start?
I can see your screen. I can hear you. I'm giving people a minute more.
Okay.
Time passes very quickly. You think you have 20 minutes. Oh, plenty of time. I'll send 2 emails and then you're still just reading the backlog. So it's right. Hello, everyone. This is just a reminder of where we are. This is day 1 of the 2-day Ego4D virtual winter symposium. Very wintry here. I'm not sure if it's wintry everywhere, but here it's been raining nonstop all day. In this session, we will have 2 talks on task graphs, both of them from the University of Catania. This talk is by Ivan, and the work was presented this CVPR. And then we have another talk, and beyond that, please stay around. We are going to have an open mic session. Particularly, we would like to hear from everyone about how this Ego4D doing, what things do you think we need to do as a consortium? How are we doing with our annotations? What are the things you think are missing? As well as insights for how we can maintain our rhythm and presence as a community, like internally within this team, as well as externally. But for now, it's Ivan Rodin from the University of Catania. Over to you.
Thank you, Dima. Hi, everyone. Today I'm going to present my work on egocentric action scene graphs for long-form video understanding. As Dima told, it was presented on CVPR this year, and this is a project which is done in collaboration with our colleagues from Intel Labs. The motivation for this work was basically in lack of structured representations in current egocentric data sets. So if we are talking about the representing of human activities, often actions are represented very simply as verb-noun pairs. For example, take cup, like in Epic Kitchens or in Ego4D. Also, there are free-form narrations, for example, textual descriptions of the activities performed by camera wearer, like camera wearer is going to the kitchen and taking the cup of tea. Sometimes in the annotations, we can also see that the active objects are grounded with the bounded boxes, so we can kind of detect the objects which is in the camera wearer hands, which he manipulates, but still it's not the structured representations which may be useful for many downstream tasks, such as captioning, anticipation, long-form summarization, visual question answering, etc. One of possible solutions may be to utilize the scene graphs, and they can be really good representations as they capture many objects in the scene, as they are really descriptive, and they capture also the relationships between objects, between camera wearer, the actions. But most of the scene graph literature is focused on third-person video datasets. Besides, most of the scene graphs they tend to describe the scene rather than action. So they describe relationships between objects. The cup is staying on the table, although the cup and table may have nothing to do with the camera wearer interest and his activities. And finally, most of the scene graphs are done for images or for really short videos of length less than 1 minute. And all of this led for us to decide that we need to create a new data set on scene graphs, but which are tailored for egocentric video understanding and in particular for long-form video understanding. And we proposed this new representation, which we called EISG, Egocentric Action Scene Graph, which is basically a temporally evolving action scene graph. So this scene graph captures not all the objects which are present in the scene, but it is centered around the action performed by camera wearer. For example, if the camera wearer takes dough, he probably takes it from container, he takes it with both hands or with right hand. Then camera wearer performs some other activity with the same piece of dough. For example, he may add flour to it, so again with some hand. And finally, he can perform something else with the same piece of dough. He can drop it somewhere, and we want to capture all the temporal dynamic of the activity performed by camera wearer with the objects that he manipulates and that he interacts with, not all the objects in the scene. And in the same time, we also want to track the objects, because if we say that camera wearer performs activities with the dough, there can be other piece of dough, there can be several objects of the same class, and we of course want to match them temporally. And if we take all of this, we combine it into egocentric action scene graph, which is temporally evolving graph capturing activities and capturing the manipulated objects or objects involved in the activities in that or another way. And to collect this data, we proposed a new annotation pipeline, which consists of 3 stages. First stage is a manual annotation, which we run on Amazon Mechanical Turk. And this annotation basically consists of extending the Ego4D annotations. So we initialize the graph from simply verb-noun pair, then we correct it if annotators find that the verb-noun pair is not suitable enough, if it's contains some mistakes or if it's not aligned well temporally. Then we add all the indirect objects. So if we take something from the table in that sense is indirect object. And then we ground all the objects with bounding boxes. The second stage consists of aggregating data from multiple annotators. So basically combining all of their annotations into one graph. At this stage, we remove the contradiction and we validate the hands with active hands, so the hands which manipulate the objects. And then there is the third stage, which we do with the SEM2 model. Basically, on this stage, we segment and track objects with the SEM2. And with this stage, we perform the temporal matching of the objects on the adjacent temporal realization of the graph. And this stage is really important if we want to have the temporal consistency of the data set. And also, it helps us to correct maybe its annotations from the annotators, because sometimes they select different words to describe the same object. So, for example, on one action, there is one action can be encoded as camera wearer cleans cutter with serviette, and there is a next action where camera wearer drops napkin. So basically, serviette and napkin is the same object here, but we need to really track it. To perform temporal matching and to see whether the object labels are more or less the same and whether the segmentation masks match or not. In the end, we got this data set, which we call Ego4D EISG. In the current version, which you can find on GitHub, it has 221 annotated sequences with a total length of 11 hours. And although it's not the biggest data set, which you can find for scene graphs, it still is the biggest one among the first-person vision data set, and it contains the longest sequences. So the average sequence length is more than 3 minutes, and on average, we have 28 graphs per sequence. The data set is pretty diverse, so it's not focused, let's say, just on kitchens, but as it's built on top of Ego4D, it is very diverse. And the temporal distribution of lengths in the graph also differs. So we have some shorter sequences of graphs, but some sequences can be pretty long and can have more than 100 graphs. Besides providing the data set and the annotation pipeline, which we also share publicly, we introduce the EISG generation task. And so first we introduce several baselines. We introduce random guess task-specific poly-connected layers, and we also adapt the baseline from third-person visions in graph generation literature, which is named STTRUN. We report this and encourage everyone to participate and to introduce their own models for seeing graph generation. Besides that, we also test whether this representation is useful or not for long-form downstream tasks. In particular, we test it on action anticipation. Basically here we verify that the egocentric action scene graph representation is basically better than verb-noun pair representation of actions. And we feed the sequences of verb-noun and the sequences of egocentric action scene graphs represented as simple text triplets to LLM and ask to forecast the next action. And we see that with egocentric action scene graphs, we can get the notable improvement over the verb-noun sequences, and we can also see this improvement if we scale the size of the sequence. So it's really, this representation can really be useful as it captures more objects in the scene, and these objects, which, for example, were not direct objects in some previous sequence of actions, they really may become the next active objects, and they can be manipulated by the camera wearer. And we also verify our approach on the task of summarization. And here again, we compare the egocentric action scene graph sequences with the sequences of verb nouns and with the sequences of ground truth narrations. And we compare them with ground truth clip summaries from Ego4D. And we see that although so this representation does not allow us to overcome to show better results than the sequences of narrations, as from them, basically the ground truth is derived, but it's still much better than verb noun, and all these results achieved without without some minimal image or visual information. And that's all. Thank you for your attention. I'll be happy to answer your questions.
Thank you. Questions? Jitendra.
So this is not, I mean, I like the work. It's nice, important. The question is, this doesn't need to be very specific for ego, right? I mean, you could do all this for exocentric video as well. So it's really, the paradigm should be viewed as general. I mean, of course, you can do it for egocentric data, you can do it for exocentric data.
Yeah, in theory, I think we can also apply it to egocentric data, but here our main difference from egocentric dataset is that we are really centered around the actions performed by camera wearer. So if there are multiple persons performing different activities, or if they exchange some objects, I mean, in theory, we can also, I mean, just add another person or another graph and connect them in some way if they, exchange some objects between each other. But as I see it for now, it's really centered around first-person vision. But yeah, I think in theory it's scalable for third person as well.
Which of the tasks did this graph thing help the most? I think you showed improvement over multiple tasks, but do they all improve similarly, or is there a particular task that benefits the most from the graph structure?
So we didn't test all of the tasks yet. So currently we're working on
multiple tasks.
Yeah, we tested short-term anticipation, long-term anticipation, and summarization. So it seems that short-term anticipation may benefit the most, as I mean, I explained you the reasons. Also, it would be interesting to test it on some sort of visual question answering benchmark. So probably this is one direction of our future work to see whether from these graphs we can ask the question, for example, where did I put this object, or where is this object come from, or how did I use this object? How did these objects interact with each other, or these sort of questions?
Thank you. And how do you deal with the famous, flower becomes dough problem, where the schematic something going to change?
Yes. Yeah, good question. So here, yeah, as I said, if we now use heuristics, right? So we use SEM2 to match the object spatially on the frame, and on top of that, we just use the matching by the object class. So if there is an object of class, I don't know, cutlery, then even if it's on dough, we will not match it with dough. But yeah, here, if we added flour to the dough, then probably it just becomes dough, and we have this node as dough, which is evolved next.
Hey, any other questions? Otherwise, thanks a lot, Ivan. Next talk is by Luigi for a work to be presented at NeurIPS, I guess also next.
Hi.
Yes, hi. We can hear you.
Yes. Can I share the screen?
Yes, you can. Hopefully you can. Just know if you can't.
Okay. Can you
Yeah,
see the screen?
we indeed can. Go ahead.
Okay. Hi all. My name is Luigi Seminara, and I'll present differentiable task graph learning, procedural activity representation, and online mistake detection from egocentric videos. The authors of this work are me, Giovanni Maria Farinella, and Antonino Furnari, which are my supervisor from the University of Catania, and this work was accepted as a spotlight paper in NeurIPS 2024. So, we worked with procedures, and examples of procedures are back repair, cooking, and health. Understanding the logical structure of a procedure is important because if we use a wearable device, it could help us in finding mistakes or suggesting the next steps. A procedures refer to a scenario like assembling a tent, while the key steps are all possible actions inside the considered scenario, such as read instructions, pretend, assemble support, etc. Suppose that we want to know all the possible ways to make an omelette. A task graph is a logical structure able to describe a procedure, so it consists of different paths and an edge that goes from a node to another to identify a precondition. For example, get a bowl is a precondition for add water, add milk, and crack egg. In Ego4D, I was involved in the team that worked on the task of procedure understanding, where we manually built graphs for a subset of procedural scenarios, and we used them to find previous key steps, procedural error, future key steps, optional key steps, and missing key steps. The baseline consists on building this graph in using creating a transitional graphs from procedures and then use them at test time. But there are other work that talks about task graphs, but this work are based on heuristic methods. An example is multimodal subtask graph generation from instructional videos and method reinforcement learning with autonomous inference of subtask dependencies. And the authors of this work considered an approach based on inductive logic programming. Other approaches for building task graphs are reported inside the paper Video Mine Task Graphs for Key Step Recognition in Instructional Videos, where the authors introduce a probabilistic approach to define an edge between two key steps, while the authors of the paper Procedural Aware Training for Instructional Video Understanding build the graphs starting from WikiHow steps ordering, and then they combine all the different task graphs for each single scenario to build a unique task graph able to describe all the scenario. We introduce a novel framework for learning task graph from action sequences, which relies on maximum likelihood estimation to provide a differentiable loss function. So given a sequence of action, the goal is to estimate the probability of the given sequence to be a topological sort of the given graph, and we can calculate it using the Zheng probability. let's consider the following graph, which is described by the following adjacency matrix. If we can estimate the probability of this sequence in a differentiable way, we can use maximum likelihood to perform gradient descent directly inside the adjacency matrix. Yes, we can do that, but the symbols are not differentiable. So the idea is that we can estimate the probability of observing a key step ki given a partial observed sequence and the constraints imposed by the adjacency matrix following Laplace's classic definition of probability. So if we take a look at the formula in the numerator, we want to answer the question, can I do step ki after doing steps kj? In the denominator, we want to answer the question, how many steps can I do besides ki? Now, this is an example to better understand the formula. The probability of start in this case is 1 because it has no precondition, while the probability of A given start and the adjacency matrix is calculated as follows. For the numerator, we examine the row of the adjacency matrix that correspond to the current action, and we then sum all the values in the columns associated with the observed key steps. If this sum is 0, we put 1 because this means that all preconditions are satisfied, and then we made the in the denominator, we consider all the unobserved key steps, and for each of them, we made the same reasoning of the numerator. So the final probability is 50%. Then, applying the same process, we calculate the probability of B given A start and adjacency matrix. And finally, we calculate the probability of N given A, B start and adjacency matrix. The final probability of the given sequence is 50%. So to enable gradient-based learning, we consider the case of the continuous adjacency matrix. All the mathematical steps required to derive the final loss are detailed inside the paper. And the loss that we obtained is a differentiable contrastive loss that where we maximize the ages between current and past steps and minimize the ages between future and past steps. We propose two approaches to task graph learning. The direct optimization of the adjacency matrix, where we initialize randomly the adjacency matrix Z, and here we simply backpropagate into the adjacency matrix, practically moving into the solution space as in classic machine learning estimation. But we propose a task graph transformer, which represents the main advantage of using our loss to learn a task graph, because we can train a model that generates a task graph starting from text description of key steps or video embeddings. Taking features as input, this model enables transfer learning, cross-model video text learning, and better generalization. The Ego4D benchmark represents a natural choice for evaluating our graph generation algorithm. To assess its performance, we conducted experiments using both ground truth annotation and predicted key steps. These results validate the effectiveness of our approach in generating reliable task graphs using ground truth key steps, while also demonstrating strong evaluation performance even when key steps predictions are noisy. Explanation of these experiments will be added to an extension of the work that we published at NeurIPS, because inside the paper these experiments are not present. We performed the experiments of task graph learning even using Ego4D, which is a collection of videos where the sequences are extracted from a recipe task graph. And we observed that our models achieves better results compared to heuristics methods that are based on heuristics. So we evaluated also TGT transfer learning capability using a leave one out approach, and we trained TGT on all procedures except one. The results in table revealed that our method outperforms competitors that lack transfer learning capabilities. And also we compare the abilities of our TGT model trained on visual features to generalize the two fundamental tasks that are pairwise ordering and future prediction. The results obtained from these experiments are better than the random ones. So TGT trained on videos shows emerging video understanding abilities. In the case of pairwise ordering, we input the model with video features from 2 key steps and get a 4x4 matrix as output, because we append start and then node to this graph, and we are interested in the value in cell 1, 2, and 2, 1, and we want that the value in cell 2, 1 is greater than the value in cell 1, 2, because take eggs is a precondition for brick eggs. In future prediction, we give to the model three video features that belongs to three steps that are take eggs, break eggs, and mix eggs in this example. And we are interested in the cell 1, 3 and 3, 1, and we want that the cell 3, 1 is greater than the cell 1, 3 because take eggs is a past key steps for mix eggs. This means that mix eggs is a future steps. Here is an example, a qualitative results of a graph that is clean and lubricate the chain from Ego4D. And the graph must be read in a bottom-up manner. So here is the start and here is the end. And we can observe that get a brush is a precondition for add degreaser to the brush. And this is a precondition for brush the chain. But also we can find other important precondition like this one or this one or this one. So the qualitative result is also good. And also we test our task graph for line mistake detection. In this image, we can see a recognition module. This recognition module make a prediction for frame level, and then we aggregate this frame to obtain a step level prediction, and then we use our task graph to find mistakes. And we conducted online mistake detection experiments on EPIC 10.0 and Assembly 1010 following the Prego protocol published at CVPR 2024. This involved using both ground truth action sequences and predicted action sequences. In the second part of the table, we can observe a drop in all the metrics of all the methods because this is due to the use of the line action recognition model. However, our approach still achieves the best results. So thanks for your attention, and scan the QR code if you want more details on our work.
Thank you very much, and congratulations. I see you've labeled this spotlight work, so well done.
Thank you.
Any questions for Luigi? I was a little bit confused about like repetitions. What if I take an egg, break an egg, and then take another egg, break an egg? Like how do you deal with like repetitiveness in this concept of
in case of repetitiveness? Okay. Okay, during the training of this model, we considered only the first action if there is a repetition, because if we take a look to the graph, in this case, if get the brush, maybe we can do get the brush more times inside our video. But these are the main precondition for get the brush. So if I repeat get the brush after these steps, it is good because get the brush satisfy all the preconditions.
I see. So if I end up putting 2 eggs instead of 3 eggs, you will consider that an error.
Yeah.
I mean, you can't help me detect my mistake if I don't get this right number. I guess.
Yes.
Do you see a potential extension where such a limitation can be removed?
Which are okay. The potential. Okay. This is for instance, one of the problem maybe is if we take a look to the results in Ego4D, we can see that the optional key steps, this method is not good maybe for optional key steps because we used I can tell a lot about the method, but we used an approach based on probability, but we can see that the results are very near to the baseline. So this method is not good for optional key steps. And also it is good if we have a representation that is able to say to us which steps are repeatable, because in this moment all steps could be repeatable. So in this case, we can catch the error.
Any other questions to Luigi? It's a chance to train him for his NeurIPS talk. So if you have questions, please ask. Okay, otherwise, thank you very much. So unfortunately, as I mentioned, the first talk